Let's start with a discussion on the Risc-V privilege modes. When we talk about privilege levels in Risc-V, it helps to picture them as these three concentric circles. At the very center is machine mode. This is the most powerful level. The firmware and the low-level runtime code live here, and they touch every part of the hardware. The machine mode has a privilege level of 3. The next ring out is the supervisor mode. This is where an operating system kernel typically runs. It has a lot of control, things like managing virtual memory, handling system calls, but it still operates under the rules set by the machine mode. The supervisor mode has a privilege level encoding of 1. The outermost circle is the user mode. The user mode is where the regular applications run. User mode has the least privilege level, which is an encoding of 0, and cannot directly access hardware or execute sensitive instructions. If the user mode code needs to access more privileged resources, it needs to make a request to the higher privilege level using an eCall instruction. So the idea behind this is fairly simple. The deeper you go into these circles, the more power and responsibility you have. This layered structure helps keep the system organized and secure. Now let's look at a formal definition of privilege mode. A privilege mode is a hardware-defined execution level that controls what instructions and resources a code is allowed to access. Here are a couple of examples of protection that is enforced by hardware using the privilege modes. Suppose we have code in supervisor mode which tries to access an M mode control register like mscratch. Since the code is running in a lower privilege mode, it cannot access the control register that belongs to the higher privilege mode. Such an access is disallowed by the processor. The other example is user mode code which tries to execute a supervisor level instruction like sfence. In both cases, the processor disallows the access by signaling an illegal instruction exception, and the control gets transferred to the illegal exception handler. Now let's briefly look at the privilege mode transitions. There are two kinds of movements. There is a vertical transition and a horizontal transition. Vertical transitions involve a change in privilege level. In the right-hand side of the screen, we can see a transition from a lower privilege level to a higher privilege level, which is an upward vertical transition. This typically happens through exceptions, interrupts, and most commonly an eCall instruction. In fact, this is how a lower privilege mode will ask for assistance from a higher privilege mode code. The other transition that we see here is a downward vertical movement, where the transition is from a higher privilege mode to a lower privilege mode. Moving downward is generally much more controlled, and it only happens when the higher privilege mode code explicitly decides to return using instructions like mret and sret. Mret and sret are typically called the trap return instructions. When the mret or sret instruction executes, it restores the previous privilege level and execution resumes where the lower privilege mode code left off when the original exception occurred. Horizontal transitions, on the other hand, don't change privilege mode at all. They are just control mode shifts within the same privilege level. Like a timer interrupt, which is handled entirely in the supervisor mode, or an SRET which returns to the supervisor mode because that's where the interrupted code was running. So the idea here is vertical transitions are accompanied by a change in privilege level. So vertical transitions change who is in charge. Horizontal transitions just change what is running. In the next video, we will look at the finer details of privilege mode transitions.